Okay, so today I'm going to continue the hash table implementation. So it's gonna be V2. So previously, what I had to done to avoid collision was called separate chaining, which basically involved that when we have an item with keys that have hash collisions, we basically store those items in a list or in a collection, as we see here. But what I'm gonna basically, like one of the problems with this implementation is that if there's a lot of collisions, and then here we have like, right, many elements, searching for an element, or deleting an element here is gonna basically be linear time. So big O of n. So one approach to solve this is to use another technique, which is called open addressing, which is another collision resolution technique. And then there's like several ones. So there's linear probing and quadratic probing and double hashing. So basically, I'm going to go for double hashing for the moment, because these ones here, so like linear probing is just a linear function, right? So we have so this typically, like this hash function will typically be the hash of the key modulo the size of the table plus our collision count, right? So what that's gonna happen. So if I just draw here like let's say our table, and for example, let's say like there's like some collision, right? There's some collision here, and when we want to insert a new element or delete, this function here will basically compute a new basically a new location on the hash table, right? Through the hash function. But since it's linear, this creates clustering, like large amounts of clustering of elements, right? So for example, all of this could be filled spots for that key, right? Because other elements probably had the same hash collision. And perhaps like at the end of this, it will be like the free space for this key, right? But then of course, to do that, we'll have to do like compute this hash function for every collision. So we will basically have to, oh my God, do this one, right? We will have to do this basically also n times, right? That will be the worst case scenario. So n times. And then that will obviously be problematic as well. And then quadratic probing is basically the same concept. I mean, it will tend to try to eliminate this clustering of keys. I don't have the formula here, but basically it's like taking, the quadratic of this function. Let's see if I can open it here. Yeah, so it's this, right? So instead of linear, the distance will be quadratic, right? So instead of step by step, it's going to be like this one will be the next sequence, and then this one will be the next sequence, and so forth. But that also tends to create like a clustering of elements in the hash table. And of course, like this could be also problematic. But again, like I don't have like a real world application for the moment. So like whatever I implement right now is like really, yeah, it wouldn't really matter. But I think one interesting one to approach or to implement is going to be the double hashing, right? So this double hashing will basically, instead of having like this quadratic or polynomial relationship or like probing jump or linear probing jump, it's going to be, so what the double hashing function does is that kind of mimics if it was more like random, right? So then it distributes the keys more evenly in the hash table. So when there is a collision, we don't have these clusters here, right? So it basically avoids them. So diagrammatically, how that basically looks like, if I copy this thing here, And let's say we have a collision of an element here, for example. The next available slot could either be like, big jump like this or here, right? And then that jump really depends on the second hash function, right? So the way this works, if I just copy this here, is that we have two hash functions. So the first hash function, which will be the same like as we usually have. So we have the hash of the key modulo m, right? Where m is the size of the table. And then we have this second hash function, right? And then it's basically multiplied by a constant. Well, it's not a constant value, but basically by the collision count. So every time there's a collision, like this value will increment, right? And it will be multiplied by the second hash function. And the second hash function is basically something like this, like 1 plus k, so the key, right? The hash modulo m prime. And typically also like m prime can be chosen. I mean, there's lots of variations of this one, right? But let's say a typical example, and this one I got from the data structures and algorithms book. I also linked in the README in the GitHub. So basically, it's set to m minus 1. So it's just one size or one value less than the hash table size. And the important things about this second hash function is that it determines the size of the jumps in the probe sequence. So that's what I was kind of like diagramming here, right? So that this one makes the size of the jumps, but then at the same time, it's depending on the hash value of the key. So the goal of let's say why basically people invented this is to try to overcome the clustering of keys and collision resolution. So that's basically what I will be implementing today. Yeah, so basically all of this is what I just explained. So those are just some of the notes I had here. And then also another important thing, although I haven't really spoken much about this, is the load factor, right? So we have the number of elements in the hash table over the hash table size. And ideally, this load factor should, of course, never exceed 1, because then we will be basically having problems in terms of, we could probably have a lot of, like, it can be full or close to full, the hash table. So for example, with insertions, they could potentially be linear time, because we'll have to do, check what slot is empty for many iterations. But ideally, like proportionally, this should basically be like below 0.75, or once we're reaching that, we have to like resize the table. But then that has other complexities. I don't know if I'm gonna be able to even start on this, like in this video, because you can imagine, like, if you want to simulate some kind of real application for this, like if the system is on load and there's like thousands of queries per second, you cannot just like create a new table on the fly. So that's like another technical detail there. Okay, so that is basically it. Another important thing is that also at most each element occupies one slot, right? Because before we had like one element can occupy, like more than one element can occupy one slot, right? Because we were having a list. But now we guarantee that there's only one element per slot, right? And then of course, that's why for collision resolution, we have to do this like probing, right? Go through each slot and say, okay, are you empty? Are you not empty? Can I like insert here, or does the element exist here or not? Okay. So yeah, I'm gonna jump over here. So here's like the updated also references. And this one is the introduction to algorithms and data structures, third edition. And then here I specify chapter 11 talks more specifically about hash tables. So there's a couple of things I have to do here. So first of all, I have this class, but then since we're changing the implementation, right? So I have to do a couple of updates here. So for now, this will no longer be lists, but it will be null. So let me just comment this out, and I'm gonna see if I can. This will remember here. Okay, Python main. Okay, so buckets. What did I call this thing? Yeah, buckets. Oops. Well, oh my God. Yeah, type today. Okay, buckets. And yeah, so it's a collection of nuns. Okay. Okay, cool. So then let's okay, we'll have to change this, of course. So for now, I'm gonna basically remove these guys here. And then I have to, so this is our hash function, but then I have to say, of course, I will have to change this. So this will have to be, okay, let's leave it at hash. And then I'm gonna say, we're gonna have the hash 1. And then I'm going, this will be this one. So of that length, and then I will have hash 2. And then I will have, let's see the formula again that I forgot. So it will be this one. Let me just copy this. So it's going to be the key. Okay. So 1 plus key. So going to be hash key. Modulo m prime. So self dot length minus 1. Okay, perfect. So that's it. And then of course, we will return this formula here. So it's going to be our new hash function. So return, and then we have this self dot hash and key. And then we have here our collision count. So we can call it count. Collision count, and in parentheses. So collision count times this thing. So our second hash function and key. And all of this is going to be modulo m. dot length. And one, just to clarify, like, of what modulo M does here is that it guarantees that whatever the output is here, it's in the range from 0 to M. That's basically why modulo M is used, right? Because that's the idea, like the output of this hash function is a location in the hash table. That means that that location has to be between 0 and the length, right? To like guarantee it's on the table. It's not like it's not going to be an index out of range. That's just basically how the modulo operator works. Okay, so now we have our, and in essence, you know, like this is actually, you know, you could argue like there's so many, you know, these functions are not really needed. So we can say like hash 1, and we can do this, and then we can also say like hash 2 equal this. We can remove this, right? We can simplify, have less lines, less clutter, and then we can just replace. So we can say this here, and we can say like this, much better. So, okay. So this is it. So we have updated here our thing, and then we can also, I think this is also, it's not a bucket really anymore. So we can say like get, we could say get slot. Okay, perfect. So that is done. I think, yeah, we could have like some with the load factor here, but I'm not gonna really, maybe I'm gonna do a note here, like to do relate load factor. Let me just put this thing here. If lets me, yep, M, sorry, N divided by M. And then we say where N, and M is table size. Okay, so what's the next thing? So now we need to insert. So we need to basically insert this thing. Okay, so the way this is going to work is, here's my insertion algorithm. So I'm just gonna copy this thing here. Just the way docstring for the moment. Okay. Okay, so let's first compute the location. So we're gonna have location. It's gonna be slot. Yeah, get slot, get location. Okay, anyway, what is slot? Slot, and then we're gonna have our key. So we have our original location. And now we're gonna say self.buckets buckets, and we're gonna say location. And then of course, if is none, right? We basically insert that element at that location. So equals, and I think I was, okay, I also need to change this actually, we'll get slots. It cannot be list, or this could be a dictionary, or none, of course. So we're gonna add this guy. So key, I also could create some object to like not repeat this right now, like every time. Well, I'm gonna leave it like that for now. And value, which is gonna be this value here. So that's gonna be our thing, and then we basically return. So that's it. So we return, and then I mean there's also one to do here. So we do handle when insertion can't happen. And this is basically, well, we will need to resize, right? Resize. So that's what I was talking about a little bit earlier. Okay. So, and then of course, if it is, so if the location is not none, so it's basically if the location is full, so we're gonna say location is full, start probing, start probing. Okay. And then we also need a stopping condition. So basically how that's gonna happen is that, like, you can imagine, let's say if I have like here like some like slots, you know, like three, let's say 6, and let's say I'm trying to insert like some element, let's just say 15, right? And then that thing, let's say, hashes to like index 0, 1, 3. Or no, I mean, let's just none, or let's say probably none. Let's say let's just suppose 15 like hashes to index 2, for example. To index 2, then we'll probe, and then okay, the next one. I mean, let's just suppose the next one is index 3, although it's not in this case with double hashing. And then the next probing will be here. So this is free, that will be inserted. So like that will be here 15. But now let's imagine we have like some other thing like 3, for example. So 3, let's say we'll hash here, but then everything is full, right? So basically we need to stop, right? Because then we'll end in a never-ending while loop. So right, because we need to do while true. I'm just gonna put that as a placeholder. We're probing, right? But then of course we need an exit condition, and the way I think that can be implemented, again, there's like several ways, but I think a clean one is to see, or a way we can detect the cycle is we have the original location, and if somewhere in the probing we hit again the original location, we know, like, you know, we hit a loop. So we can create the other positions, but actually we can just create it here. So you can call it delta position, and or delta location, maybe don't say about position, location. Okay, so we're gonna say while location does not equal delta location, so we compute. So we will compute the new hash key. So one thing as well, collision count. Of course, I need to pass this argument as well. Collision count. So we have get slot. So collision count. This is the first one. So of course it will be 0, right? So this, of course, the first one, this all will be 0, and we'll only have like our hash 1. So it will always use the first hash function in the first iteration, the first attempt. And so maybe we can decide, say, have a variable here called this one, and we can set it to 0, just pass it in here, so we can reuse it. And then let's just say increment the count. Maybe here, actually. Or we have one collision, so we can increment it here, perhaps. And then we can also increment here, because then this will be 1. Okay, so that we compute the new location. And actually, I want to rename this to get location. Location. We just get location. Perfect. And we also do the same. We call this function here. So it computes the new location based on the collision count. And then this will be added. And then we say the same thing. So if it's none, we basically add this and we return, right? And then we increment the size. We increment the size here. Okay. Okay, perfect. So of course, this and drop this comment here because it's more relevant here. Although this shouldn't really happen here, like I think we should somehow keep track at some point of about the delta. Sorry, not the delta, sorry, the load factor. And if the load factor so it should be kept smaller than 0.75. Okay, so if the load factor is like approaching 0.75 or equal to 0.75 or well, not equal, but let's say larger than 0.75, then we will like, yeah, like resize. So anyway, but I'm just putting it here just for now. Okay, perfect. So we have insert. So this looks good. So let's just do some tests here. So, so I'm just gonna run this. Collision count. Where is it? Look up. Okay, yeah, missing something. Get 20, line 24. Oh yeah, of course, I forgot to pass it. So let's pass it here. Okay, so let's run it. This must be integers or slices. Ah, I said get location. Oops. Yeah, that's okay, I see. Oh, of course. So not this actually. That was stupid. So we return. It's not a hash. So we return location actually. Or actually, we don't need this. We can actually remove this. We can remove this thing. So we can remove, it's not really needed actually. So we can just say hash. We compute the hash. This is better. Okay, cool. And assertion error, lookup size equals. Okay, there's an assertion error. So let me print. Let me print this and see what happens. So yeah, I have my item here. So I'm wondering why this is not updated. Self.size plus equals 1. Oh, of course, because it's the first element. So I have to do this, right? Of course, boom. Okay. So now it should work. Okay, excellent. That's now there's actually one thing I want to kind of print here. I just want to make sure. Okay, location. So we have location 9, location 3. So this is quite interesting. I'm wondering why am I getting different values here. That is very interesting. Let me just do this for a moment because this should be 0. So okay, let me do it here actually. So clear. There's no clear here, of course. Okay, anyway. Boom, boom, boom. So let me just say, for example, hash, and then I think I have here, what is it? Foo. And then we have modulo. What is it? What did I put here? Modulo 10. Okay. So then we say 7 modulo 10. Yeah. But this hash always returns the same. Foo. So I'm wondering. 0. I'm wondering why I always have a different location. Now I have 4. Yeah. Okay, not 100% sure, but I think that really matters, right? I thought that hash should always be the same. Okay. I'm kind of tempted to do this. 5, 0. Okay. And let's say also want to print 12.length and see, should be the same. 12 length. Yeah, 10, of course. Of course. Okay. Well, I'm gonna ignore that for now and see. Whether they become a problem. Okay. So okay, we have this perfect. And then we have as well. Actually, I also want to do the following. I want to see this test as well. I want to test the following. So let's say I want to add the same key. It will be true. And we should, as soon as like this, then let's also print. Okay. Yep. So it's behaving as expected. It doesn't keeps the same thing. It doesn't add anything. So it already exists. Okay, nice. So yeah, of course, this should be size 2. Okay. Okay, so this looks good. Okay, now I want to just change this a little bit because I want to just see the collision stuff, and it's easier to basically do with integers. So I'm going to change this so it's smaller. Okay, so for example, the first switch it here. So I'm going to say the key. So the first one will be 5. So we delete this. I'm gonna try to simulate some collisions here, hopefully. Okay, so this is it. And then let's do the other ones. So then this is gonna be 4 here. Let's just that. We got 4. And then we have put 10. So 10 will basically create a, right? So we will do like, I mean, hash will be, 10 modulo 5, and we're gonna like just, go through this formula, and it'll give us a location mapped to somewhere here. So let's see. Okay. So let's in fact just do it really quick because I want to see. So here, for example, if we have, yeah, let's reuse this. So for example, H1, if there's 10 modulo 5, we have this, and then we have H2, come on, H2. We have 1, and then we have 10 modulo 4 because it's n minus 1. And then we have here our index. And then we print the index. So the index should be 3. 0, 1, 2, 3. So in this case, it's not occupied. Not occupied, right? So let's throw 10 in there. Okay. What happened? Seems like it didn't work. Something there is broken. It should be index 3. What are we getting here? I also lost track of time here. I don't know when I started. I didn't keep track of when I was starting. So let's print here. Let's see what's wrong. So okay, I'm gonna just do an F string here. Formatted string. So it's gonna be location. And then E. Let's see, something like that here. Okay, so collision. I'm wondering here. So print. See. So yeah, we have this one here. Not any key. Why is it not? Hmm. Hmm. Kind of tricky here. Ah, okay. Oops, made a mistake. Stupid thing. Delta. It has to be delta location. Oh my God. Okay, delta location. There it is. So okay. So I think now this should work. So still not working. Why? Why not? Let me print this thing here. Print delta location. Come on. Delta location. So this is like hashing to the same thing. Hmm. Why? So it's hashing to the same location. Oh, well, why? That's weird. Hmm. I wonder why. Hmm, let's see. Hash two. Hmm, what is hash two? Hashing two. See. So hash two. This should be. Why is it hashing to that? To zero. This should not be correct. Um. Okay, let me say collision count here because we should have one. One. Collision count 0, 0, 0. The collision count one is here. Okay. Collision count one, perfect. So then let's see. Why is that 10? Let's see here. So why is it giving me 10 modulo 5? 10 modulo 5 is 0. Perfect. And then we have 10 modulo 4. 10 modulo, that should be 3. Mhm. Okay, let's see. This shouldn't be it. 10, 5, 10, 4. So that is 3. Let's run this again. Okay, so it seems like, yeah, I needed here some parentheses, but like the terminal I did not. Okay, so yeah. Oh my God, this is the thing. Yep, so parentheses, order of operations in this case. Okay, cool. So yeah, delta location 3, which is as expected. Ah, I see. It's because here I didn't do that. Okay, that was really stupid. That was really stupid. Okay, yeah. So it's perfect. So this is it. Here. Okay, cool. So yeah, handle blah, blah, blah. Okay, so this is fine. This is working as expected. So we have here 10, and then let's add the other thing here. So it's gonna be it's at 11. So I think that's why we're getting the incorrect. Yeah, that's why. I was also those hash functions were not working correctly at the beginning. I wasn't getting consistent numbers, that's all I can imagine. So the 4. So okay, cool. So we have here key 11. And then let's insert key 3, 0, 1, 2, key 3, or key. I think it should be key, well, let's just say key 2 or key 3, perhaps. Key 3. So key 3 should map to index 3 at the beginning, 0, 1, 2, and 3. So I think key 3 should then be placed at none here when we're like doing the probing. So yeah, key 3 will be placed here, right? 0, 1. Because key 3, right? So we have here first delta location, right? So our key 3, so we have our location is first 3, right? 0, 1, 2, and 3. But then this was occupied. And then after probing, we said, okay, delta location is 2, right? 0, 1, and 2, which was where none was. And that's where we add 3. And now, of course, our table is full. So if we say like just have 0, for example, should be 4, still 5. So yeah, exactly. Okay, so we know now that the probing thing here is working. So that's good news. So now I'm going to implement the search. Well, I named it get. So I'm just going to also put this here just before with the leads. So let me just say search will be better. Key. Okay. So the algorithm will be similar. So let me erase this here and go to this Notion doc. And I'm gonna paste this. Okay, so compute. Okay, so it's the same thing. So we can recycle some of this stuff. Let's see if we can later do some abstractions if it's worth it. So collision count, okay, fine. So is not, so it's not none. We know we found it. So we return this, and then we say value. So we return the thing. Okay, perfect. So it's basically what that means here is that we search directly for the element and that element was never needed to be probed. So it's exactly at the same, at the home location. I'm even tempted to actually rename this to home location, actually. Makes more sense. So home location, cool. So we have home location, we have look, and then this here we can also name to home location. Home location, cool. Okay. If not, we will do the same thing, right? So I'm just gonna reuse some of this. So let's look here. So we have delta location. So collision count, again, home location, blah. We have our collision, our new location. So our delta location. So if is not none, right? This condition is basically changed. We return. We return this, otherwise we keep incrementing collision count. And if definitely we did not find anything, we return none. So that's the search algo. Okay. Okay, cool. So that seems, so let's test this. Let's test this right now. So for example, let's look up. I'm gonna say lookup dot search, and let me look up, for example, let's look up 5. Let's look up 5. So that's our key, and then we need to assert. So say result R does not equal none. So we should have it here. So okay, perfect. So it does not equal none. And now we say like assert. We can here say 25, for example, and assert is none. Well, R is none. Okay. So assertion error. Assertion error. Ah, okay. It's because I forgot something extremely important. And we say and dot value dot key equals key. That's what it has to be. So now it's because, for example, like what would this be, like 25, right? We're searching, like give me an element with that key. Like with, you know, with when we're doing modulo, like 25 could be, for example, like wait a minute. Actually, I don't think that will solve it. Yeah, of course. Oh, yeah. Okay, this is interesting. Delta location. So let me print your delta location actually. Delta location. Uh-huh. Yeah. Okay, yeah, sure. I forgot to do it. This has to be up here. It's kind of very difficult actually to to program like this, like talking all the time. It's much better like internally doing the talking. Okay, but anyway. So self.buckets is not none, and self.buckets allocation equals key. We return the value. So yeah, basically like 25, and after doing the module, that we were basically returning some of these, one of these keys. But then of course we were or items, but we're not saying like, okay, sure, it exists, but make sure the key equals like 25. So it was returning, I don't know, like an item with key 3 or something. So that's why it wasn't working as expected. So now it should work as expected. Unbound local error cannot access local variable delta location, of course, because it shouldn't be here. Perfect. So that is it. That is it. So also you can imagine if we can't find anything. So if there's no key, this means that this will basically run in linear time, I believe. Like if a key is not found. If a key is not found, this will be running in linear time, which I don't know if it's actually, I don't know if this is actually a correct implementation. I think there should be something else. I think we should say there should be something else actually, because also this is the case where it's full. We should say like the case where like actually the home location is none. So like if the home location is directly none as well, so there should be another base case. So self-locate home location, if it's none, like that thing doesn't exist. So we should just return none, right? And then here we have the other condition. Okay, sure. Let's say, okay, it's not none, so there's some value in that home location. Does that value have the key you want? It does, so we return. And then here we have to say the same. So if in whatever probe locate, new location, we have to do the same here. So this should be the other, like, so we exit quickly. So we say is none, we basically return none. So I just want to print, I just print here. I just print collision count here, and I'm gonna remove this statement, comment it out. And I have 1, 2, 3, 4, 5, exactly, like we have 1, 2, 3, 4, 5. So it went all through them because nothing exists. But if we add this, for example, in the case where it's empty, of course, like this is not going to. Okay, but this works here. This is not gonna do anything in this case. So that's the thing, right? That I was saying, like basically our table right now, so our load factor is 1. And that's where things get really bad, because you can, like if these tables, the load factor, as the load factor reaches 1, we have these horrible scenarios, right? So for example, here, like this is basically unavoidable. Like we have to, right? Like the worst case scenario on searching or even deletion or on anything like search and deletion will be linear time. because you have to like probe everything until you hit a cycle. And that's terrible. And that's because the table is full. So that's another demonstration. This could never, should never happen. So yeah, so yes, that's actually very good. Very good. Yep, we're basically recapping that statement, making it very clear. So when table is, so when load factor, when factor which approaches 1 or is 1, search is big O of n. Okay, so that's the thing. Okay, cool. So let's now, I am going to remove this garbage here. Remove this garbage. Okay, search, delete. So there's a thing here with delete. And the thing, it needs like a different implementation, because we can't just delete. I can't just delete, for example, this element here, because when I'm searching for an element with a given key, I would probably have to go like step through this element, and if it doesn't exist, then I cannot delete it. Or sorry, like searching. So if it's none, like I assume it doesn't exist. So for example, this will return and not. But let's try that. Because for example, when I inserted 10, the initial location was 2, 0, 1, 2. Or where was it? No, it was 3, sorry. 0, 1, 2, 3. And then I had to put it to 2. So if I delete 10, for example, if I delete 10, it will be none. And then if I look up for 3, I'm just gonna copy this thing here so it's maybe more clear. So for example, delete. So if I delete 10, so again, like this item 3 was supposed to be here in where 10 is, but since 10 was there, like that previous available slot here was none. So 3 was there, was put here. So if I delete, let's say if I delete this 10, right? If I delete 10, I want to say none. So if I delete 10 and we have here, and then I search for 3, after deleting, I come here. So home location is none, right? So we'll hit home location. So home location will be none, so we return none right here. But actually, 3 is here. So we will never reach 3. So that's like an edge condition that has to be handled when deleting from hash tables. Okay, so let's do that right now. So the way that will be implemented, that we should have like something that's called deleted. So if it's deleted, we still keep searching. So I'm tempted to like, yeah. I'm tempted to make like some class, right? So is there like some lightweight? Yeah, I think there's like a data class thing. So class solid data, and what's the dictionary called? Data class. Let me see, quick fix. From classes, import data classes. Okay, cool. And then we're gonna have, so we're gonna have the key, which is any. We're gonna have the value, which is any. and we're gonna have the is deleted. So there's gonna be a Boolean, and it will be false. Okay, and then we're gonna have self dot key equals key. Okay, is deleted here. Okay, so that's basically what is going to hold these things. So let me put this here. The hell? I'm wondering if can I do this? None in Python. Yeah, it seems like I can. Okay. But then these things are gonna be probably stored in the heap all over the place. It doesn't matter. Okay, okay, let's keep going. So get search. Okay, okay, cool. So insert. So now I'm gonna replace this. I'm gonna say data. So key value and is deleted. Okay, fine. It's like this. Perfect. And we are going to be here. Perfect. So search. So home location. And we're gonna say dot key. Or let me just, I don't like this doing this repetition so much. So I'm gonna say home location. And actually, this I don't need this. I don't know, like list of these things here. Yeah. Okay, cool. So surprised it didn't return an error, but I think that's how Python is basically. So we have here it will be none or it will be data. Cool. So we have if data is none here. Okay, perfect. Now we say much cleaner value. And I can do the same thing here. So I'm gonna just say data. Okay, make this shit here. Boom. Okay, data. Oops, the key. Crap. And then data.value. So data.value is here. Perfect. Okay, perfect. Done. So I think this is it. I mean, I'm just gonna run these tests to make sure nothing is broken. Okay, perfect. Nothing is broken here. Now I forgot. How can I want to Google this? So Python class to string. Let's see, blah 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 blah. String. What is the ocean class within of this string and reper method? The preceding example demonstrated the default of reper for the object, the true string with only the class and the object ID in a hexadecimal format. Okay, let's just say string here. I'm just gonna copy this thing. Okay, fine. What's up with this? Deleted. Okay. So we're gonna say key. And then we're gonna say value. Value, and what I can add like. Okay, so now I'm gonna run this again. Well, I don't know why it didn't do this actually. I thought that it done it. Print C. Yeah, here it is. Ah, okay. That has to be like a string. Here we're gonna do it automatically. Okay, let me I see. That's because I would have to print this thing. That's kind of annoying. I don't want to like have a print function. Yeah, okay. That's a little annoying. Yeah. Okay, I'll have to Google this crap. I want to do it now. Okay, anyway. Okay, we'll have this, so is deleted. So what we will do here, so we will still like reuse some of this search stuff. So collision count. Let me just get these guys here. So then let's say we search. So if data is none, can we delete it? So let's assume data is none. So of course we return false. In case like we're trying to delete something that doesn't exist in its home location. Otherwise, we have these guys here. We have these guys here, data, that's a location with them. So get these guys here. I'm gonna say else. Okay. So if data is not none, that basically, yeah, you have to do the other one. So if data is not none and data dot key equals key, will we return true or not? Anyway, let's just return something for now. So we are going to say, so data dot is deleted equals true. Okay. So that means that this thing here, okay, I'm just gonna like make this as if it was deleted here. So this deleted is true. So then when we're searching, so we none. Oh, and so I have to update this as well. So and data dot is deleted is false. We return the value. And then here I'm gonna say if data is not none and data key and be nice to have like some kind of like can return. Okay, the function can return. Or can, yeah, anyway, let's see. Okay, so we have this and data is not none and data that key equals key. Data is deleted equals true. But then kind of also tempted to say and data that is deleted is false. In case like we don't want to like Maybe also we could also have this condition here where data it has already been deleted. We say return false. These base conditions. So first, the thing we're trying to delete does not exist. The second is the thing we're trying to delete does exist, but it has been previously deleted. And the other one is that the data it exists, and it hasn't been deleted yet. So we mark it as deleted, and we basically just return. Okay. So here, for example, is 3. So if data is none, return false. So we return false. If data is not none and data that key equals key, so we continue. We continue this. Okay, I think this should work here. So we say return if data not and data key equals key, and data that is deleted so we're gonna delete this thing equals true, and then we basically return true, and I'm going to increment here or decrement the size with the element number. So we get here. Okay. Size -1. And I think I'm gonna stop it here because the video is probably getting very long, and I want to get back.